What if I told you that right now, as you're watching this, there are places in the universe where the fate of entire stars hangs in the balance? Not just one or two, but countless celestial bodies at a crossroads, each moment a tipping point between creation and chaos. Picture this: vast clouds of cosmic dust swirling in the darkness, pregnant with possibility. Some will collapse under their own weight, igniting into blazing new suns. Others will dissipate into nothingness, their potential forever unfulfilled. These are the cosmic crossroads, 28 pivotal moments where the universe itself seems to pause, take a breath, and decide the destiny of galaxies. It's easy to forget, staring up at a quiet night sky, just how dynamic and dramatic the cosmos truly is. Out there, beyond what our eyes can see, titanic forces are at work. Gravity tugs at tendrils of gas, sculpting them into stellar nurseries. Magnetic fields twist and warp, channeling energy like invisible rivers. And in the heart of these swirling storms, something miraculous happens. A star is born. But here's the thing: not all stars are created equal. Some blaze to life with ferocious intensity, while others flicker meekly into existence. The difference. It all comes down to those critical moments at the cosmic crossroads, where the tiniest variation can lead to wildly different outcomes. This isn't just a story about distant balls of plasma. It's a story about how the universe writes its own destiny. Every galaxy, every solar system, every planet, including ours, owes its existence to these celestial turning points. So today, we're going on a journey. We'll venture into the heart of collapsing nebulae, witness the birth of stars in real time, and uncover the hidden forces that shape their fates. By the time we're done, you'll never look at the night sky the same way again, because once you understand the cosmic crossroads, you'll see the universe for what it truly is, a place of endless wonder, where every moment is a chance for something extraordinary to begin. To understand how a star is born, we have to venture into the heart of cosmic nurseries, vast, turbulent clouds of gas and dust drifting through the void. These molecular clouds, often stretching hundreds of light years across, are the cradles of stellar life. But what transforms these cold, dark regions into brilliant beacons of light? It all starts with gravity, the universe's ultimate sculptor. Imagine a single dense pocket within the cloud, where atoms and molecules huddle closer together, pulled inward by their own collective weight. Over time, this pocket grows denser, hotter, and more unstable, like a pot of water nearing its boiling point. Yet gravity doesn't act alone. Magnetic fields weave through these clouds like invisible threads, guiding and resisting the collapse of matter. Temperature plays a crucial role too. Some regions remain too warm to condense, while others cool just enough to surrender to gravity's pull. It's a delicate dance, and the slightest imbalance can mean the difference between a star that burns for billions of years and one that never forms at all. At the center of this chaos, a protostar emerges, a newborn stellar object still gathering mass. Swaddled in a swirling disk of gas and dust, it feeds voraciously, growing stronger with each passing moment. But even here, the path forks. Some protostars accumulate just enough material to ignite nuclear fusion, lighting up as full-fledged stars. Others stall, becoming brown dwarfs, failed stars that glow faintly before fading into obscurity. The key to unlocking these mysteries lies in the protostar's early environment. Astronomers study these infant stars using infrared telescopes, piercing the dusty shrouds that hide them from visible light. What they've found is astonishing. No two stellar nurseries are alike. Some regions produce massive stars that live fast and die young, while others spawn smaller, steadier suns like our own. So the next time you gaze at the night sky, remember, every star you see was once a fragile spark, born from chaos and chance. Their stories are written in the swirling dust of cosmic crossroads, where the universe makes its most fateful decisions. Cosmic crossroads aren't just poetic metaphors, they're real, measurable turning points where the fate of a star is sealed. Think of them like a choose-your-own adventure book written by the universe itself. At each of these 28 pivotal moments, the conditions in a stellar nursery, turbulence, radiation pressure, even the gravitational nudges from nearby stars, push collapsing gas and dust down wildly different evolutionary paths. One cloud might fragment into a cluster of modest stars, while another, under nearly identical initial conditions, births a single colossal giant hundreds of times more massive than our Sun. Take turbulence, for example. In a molecular cloud, chaotic motions act like an invisible mixer, stirring the gas into denser clumps. Too much turbulence, and the cloud resists collapse entirely, scattering its potential stars to the cosmic winds. Too little, and the entire cloud might collapse into one monstrous star, leaving no material left for smaller siblings. It's a Goldilocks scenario. Just the right amount creates a balanced stellar family. Then there's radiation, the silent sculptor. Young, hot stars don't just shine, they flood their surroundings with intense ultraviolet light, eroding nearby gas clouds like sandblasters. This feedback can shut down star formation in one region while triggering it in another, carving out bubbles where new stars ignite along the edges. In some crossroads, this radiation is the deciding factor between a star-rich cluster and a barren void. Even the neighbors play a role. A passing star or the shockwave from a distant supernova can compress a gas cloud just enough to tip it over the edge into collapse. These chance encounters mean two nearly identical clouds light years apart can end up producing entirely different stellar populations. Astrophysicists have mapped these crossroads by studying thousands of star-forming regions, piecing together how slight variations lead to staggering diversity. Some pathways lead to blue supergiants that blaze brilliantly and die young in supernova. Others produce red dwarfs so faint they'll outlive the galaxy itself. And tucked between these extremes are stars like our Sun, middleweights born from a precise sequence of cosmic decisions. What's truly humbling is realizing these crossroads don't just shape stars, they shape futures. A massive star's death seeds the galaxy with heavy elements for planets. A quiet red dwarf might host a habitable world for trillions of years. Every flicker in the night sky is the product of a chain reaction that began at these critical junctures where the universe time and again faced a choice and chose to create. Among the 28 cosmic crossroads, none is more fundamental than the very first, the moment when a molecular cloud stands on the edge of becoming something more. These colossal structures, drifting like ghostly islands in space, hold the raw ingredients for star formation: hydrogen molecules, dust grains, and trace elements forged in ancient stellar explosions. But here's what's fascinating: not every cloud gets to graduate into a stellar nursery. Their destiny hinges on a fragile equilibrium between collapse and dispersal, a cosmic coin toss where density and composition call the shots. Picture a molecular cloud as a vast, chaotic metropolis. Some neighborhoods are crowded and bustling regions where gas particles jostle so closely together that gravity gains the upper hand. In these dense pockets, atoms begin a slow but inevitable inward spiral, drawn together by their collective pull. But other areas resemble quiet suburbs where particles drift too far apart to ever coalesce. External forces like radiation from nearby stars or shockwaves from supernova can sweep through these sparse regions, scattering their potential before gravity even gets a chance to act. Turbulence adds another layer of complexity. Imagine stirring a cup of coffee. Those swirling eddies mirror the chaotic motions within a molecular cloud. In some cases, turbulence acts like a cosmic blender, churning the gas into knots dense enough to trigger collapse. But too much turbulence can have the opposite effect, keeping particles too agitated to settle. It's the ultimate balancing act, just enough motion to create structure, but not so much that it tears everything apart. Scientists study these variations using radio telescopes, which peer through the dust to map the invisible architecture of these clouds. By analyzing subtle differences in density and motion, they can predict which regions will likely ignite into stars and which will fade quietly into the void. What they've discovered is startling. The fate of a star isn't decided when nuclear fusion begins. It's sealed much earlier in the silent, invisible struggle within these clouds. A slight increase in density, a chance encounter with a passing shockwave, these tiny factors cascade into monumental consequences. So when we look at a star, we're not just seeing a ball of plasma. We're witnessing the aftermath of a decision made in the cold, dark depths of a molecular cloud where the universe weighed the odds and chose creation over oblivion. Magnetic fields are the universe's invisible architects, silently shaping star formation in ways we're only beginning to understand. Picture a river flowing through a canyon, except instead of water, it's lines of magnetic force threading through cosmic clouds, directing where and how matter collapses. These fields don't just passively exist, they actively wrestle with gravity, sometimes working as partners, other times as rivals. In one stellar nursery, a magnetic field might act like a scaffold, providing structure that lets gas accumulate gradually into a single massive star. Just a few light years away, those same forces could twist and tangle, splintering a cloud into dozens of smaller fragments, each destined to become its own star. The strength of these fields is astonishing. Some are thousands of times more powerful than Earth's magnetic field, yet their influence is subtle, operating on scales so vast it's like watching a slow-motion ballet. As gas particles spiral along these invisible lines, they create intricate patterns resembling the swirls of cream in coffee. In some regions, the fields act as brakes, slowing collapse and preventing chaotic fragmentation. This can lead to orderly, long-lived stars like our Sun. Elsewhere, when fields become knotted or misaligned, they trigger turbulence, shredding clouds into stellar siblings born in rapid-fire succession. Astronomers detect these hidden forces by studying the polarization of light, how dust grains align with magnetic fields like microscopic compass needles. What they've found is revolutionary. Magnetic fields don't just influence star formation, they dictate its rhythm. A cloud with strong, orderly fields might produce a solitary giant star, while a weakly magnetized one could erupt into a bustling cluster. Even more fascinating, these fields can stretch light years across a nursery, linking the fates of stars that haven't even ignited yet. Consider the Orion Nebula, a nearby stellar factory where magnetic channels funnel gas into dense filaments. Here, the fields act like cosmic conveyor belts, feeding material to young stars at precise rates. Without this regulation, the nebula might have birthed stars too quickly, depleting its resources before planetary systems could form. It's a reminder that magnetic fields aren't just part of the story. They're the unseen hands sculpting the diversity of stars we see today. So when we marvel at the night sky, we're not just seeing points of light. We're witnessing the aftermath of an epic struggle between gravity and magnetism, a battle where the slightest shift in balance changes everything. The stars we know and the worlds that orbit them owe their existence to these invisible forces, quietly guiding the universe's greatest act of creation. Radiation pressure is the universe's paradoxical force, a power that can cradle newborn stars or tear their nurseries apart. Imagine a fledgling star just beginning to shine. As nuclear fusion ignites in its core, it doesn't just emit light, it unleashes a hurricane of energy, blasting ultraviolet radiation and charged particles into the surrounding cloud. This stellar wind should, in theory, sweep away the very gas and dust that feed its growth. Yet somehow, against all odds, star formation doesn't just survive this onslaught, it thrives because of it. Take the Eagle Nebula's iconic pillars of creation, towering columns of dust where stars are being born even as radiation erodes them. Here, the intense light from nearby massive stars acts like a cosmic sculptor, carving away loose material while compressing denser pockets. The pillars aren't just passively dissolving their incubators, they're shielded cores collapsing into new stars under the pressure of the radiation itself. It's a delicate equilibrium. Too much radiation and the entire structure disintegrates. Too little and the gas remains too diffused to collapse. But radiation's influence doesn't stop at sculpting. In sprawling stellar nurseries like the Carina Nebula, shockwaves from brilliant, short-lived stars trigger chain reactions. When a massive star's radiation slams into a neighboring gas cloud, the impact can squeeze the material just enough to tip it over the edge into gravitational collapse. Entire generations of stars owe their existence to this domino effect, one star's birth catalyzing another's. Yet there's a darker side. In regions where radiation runs unchecked, it can sterilize vast swaths of space. The Orion Nebula's trapezium cluster, for example, hosts stars so luminous their combined output has blown a cavity clear of gas, leaving a sparkling but barren core. Future star formation here is impossible. The raw materials have been exiled into the void. Astronomers call this feedback loop the stellar birth-death cycle, and it's the reason star clusters have such varied personalities. Some, like globular clusters, are ancient relics where star birth ceased eons ago under relentless radiation. Others, like open clusters, are bustling nurseries where radiation's push and pull sustain ongoing creation. This cosmic tug-of-war even shapes planetary systems. A star's radiation determines how much material remains for planets to form, and what kind. Too aggressive, and only rocky worlds might coalesce before the gas is stripped away. Too gentle, and gas giants could dominate. Our own solar system's mix of planets might trace back to the precise balance of radiation pressure in its long-vanished nursery. So when we gaze at a star, we're seeing more than a ball of plasma. We're witnessing a survivor and a catalyst. Every flicker of starlight is part of an eternal conversation between destruction and creation, where the universe writes its next chapter one photon at a time. Chaos and creation might seem like opposites, but in the cosmic dance of star formation, turbulence is the wild card that reshapes destinies. Picture a molecular cloud not as a placid pool of gas, but as a storm-tossed ocean, with waves of chaotic motion crashing through its depths. This isn't just random noise, it's a fundamental force that decides whether a cloud will birth a bustling stellar family or a handful of solitary giants. When turbulence runs high, gas fragments into countless clumps, each collapsing into its own star. The result, clusters bursting with activity, like the Orion Nebula's stellar metropolis, where hundreds of young stars jostle for space. But in calmer regions, gravity works undisturbed, pulling vast amounts of material into a few massive stars that dominate their surroundings. The origins of this turbulence are as varied as their effects. Sometimes it's sparked by supernova shockwaves rippling through the galaxy, like a stone thrown into a pond. Other times, it's the gravitational pull of passing galaxies or the sheer energy of newborn stars themselves, their stellar winds stirring the cosmic pot. Even the rotation of the galaxy contributes, twisting gas clouds into spirals of motion. What's fascinating is how these chaotic forces leave fingerprints on the stars they create. In highly turbulent nurseries, stars tend to be smaller and more numerous, their orbits scrambled by the violence of their birth. Calmer environments, by contrast, produce orderly systems where massive stars anchor quieter neighborhoods, much like our own sun's relatively peaceful origins. Astronomers measure this turbulence by studying the subtle shifts in light from molecules within these clouds. The wider the spread of velocities, the more chaotic the environment. And the data reveals a startling pattern. Galaxies with active star formation often have clouds that are veritable maelstroms, while dormant galaxies drift in eerie calm. This turbulence crossroads doesn't just shape stars, it shapes entire galactic ecosystems. A turbulent nursery might flood its galaxy with ultraviolet radiation and heavy elements, while a serene one leaves behind a quieter legacy. Yet turbulence isn't just a destroyer or a creator, it's a regulator. Without it, gas might collapse too efficiently, forming monstrous stars that burn out quickly and leave little behind for planets. Too much, and stars might form too small and faint to ignite the chemical richness needed for life. Our own solar system's existence could hinge on a Goldilocks level of turbulence in its ancestral cloud, balancing chaos and order just right. So when we look up at the night sky, we're seeing the aftermath of these invisible storms, the fingerprints of turbulence written in starlight, a reminder that even in the cosmos, a little chaos can be the mother of creation. At the heart of every stellar nursery lies a silent question. Will this collapsing cloud of gas and dust forge a solitary star, or will it split its birthright between twins? This fifth cosmic crossroads hinges on a deceptively simple factor: spin. As a molecular cloud contracts, even the faintest rotation amplifies, like a figure skater pulling in their arms to accelerate. If that spin grows unchecked, the cloud can't collapse into a single point. Instead, it flattens into a whirling disk that eventually fragments, birthing not one star, but two or more locked in an eternal gravitational embrace. Binary star systems aren't just common, they're the universe's default setting in many regions. In the Orion Nebula's bustling stellar factory, over half of all newborn stars have companions. Yet just a few hundred light-years away, in quieter nurseries like Taurus, solitary stars dominate. The difference often comes down to turbulence. Highly agitated clouds tend to fracture into multiple dense cores during collapse, each becoming its own star. Calmer environments allow gas to spiral smoothly toward a single central point. But this split isn't just about numbers, it reshapes cosmic destinies. Binary stars live radically different lives than their solitary cousins. Their gravitational tug-of-war can stretch protoplanetary disks into bizarre shapes, altering the very architecture of potential solar systems. Some binaries orbit so closely they'll eventually merge in spectacular explosions. Others steal material from one another, triggering unpredictable outbursts. And then there are the rare pairs where one star collapses into a black hole, slowly consuming its partner over eons. Even more fascinating is how this crossroads echoes across time. A solitary star like our Sun offers stable orbits for planets with relatively predictable energy output. But in binary systems, planets face a chaotic environment, gravitational kicks that might fling them into deep space or send them crashing into their host stars. Yet some worlds orbit binaries at just the right distance, basking in double sunsets. These are the ultimate cosmic wildcards, where the simple act of a cloud's fragmentation billions of years ago writes the fate of countless future worlds. Astronomers trace these diverging paths by studying stellar nurseries across the galaxy. In regions like Rho Ophiuchi, they've caught protostellar disks in the act of splitting filaments of gas pinching off to form secondary stars. Other observations reveal failed binaries, pairs that drifted apart when passing stars robbed them of their gravitational bond. Each discovery adds another piece to the puzzle of why some stars go solo while others thrive in pairs. So when we look up at Sirius, the brightest star in our night sky, we're actually seeing a binary system, a luminous primary star with a faint white dwarf companion. Their story began at this very crossroads where spin and chance conspired to create not one star but two. And across the universe, countless other stellar siblings continue this dance, their fates sealed by the whirl of gas in an ancient collapsing cloud. Supernova are the universe's ultimate double-edged sword, cataclysmic explosions so powerful they can either spark stellar birth or snuff it out entirely. Imagine a dying star having burned through its nuclear fuel, suddenly collapsing inward before rebounding in a shockwave that rips through space at millions of kilometers per hour. When this wall of energy slams into a nearby molecular cloud, the impact does something extraordinary. Gas that was once too diffused to collapse under its own gravity gets compressed like a cosmic accordion, triggering a chain reaction of star formation. The Eagle Nebula's famous pillars, for instance, might owe their star-forming peaks to shockwaves from long-dead giants, yet not all clouds survive the encounter. Some are torn apart by the violence, their potential stars scattered into the void before they ever ignite. It's a brutal lottery, one that depends on the cloud's distance from the blast, its density, even its magnetic fields. The same supernova that breathes life into one region could sterilize another, leaving behind nothing but a hollowed-out bubble of hot gas. But the legacy of these explosions goes deeper. As the supernova's shockwave expands, it scatters heavy elements forged in the star's core: carbon, oxygen, iron, seeding the surrounding space with the building blocks of planets and life. Our own solar system likely formed from a cloud enriched by such an explosion. The iron in your blood, the calcium in your bones, they were once stardust flung into the cosmos by a dying sun. Astronomers have traced these cycles of destruction and rebirth across the galaxy. In the Orion Arm, vast stellar nurseries like NGC 2632 show clear evidence of supernova-triggered star formation, with young stars aligning along the edges of ancient blast waves. Meanwhile, regions like the local bubble, a cavern of sparse gas surrounding our solar system, bear the scars of past explosions that cleared the stage for future creation. Perhaps most remarkable is the timing. Supernova don't just alter space, they manipulate time, by jump-starting star formation in some areas while delaying it in others. These explosions create generations of stars with wildly different fates. A cloud compressed by a supernova might birth stars billions of years earlier than it otherwise would have, altering the chemical evolution of entire galaxies. So when we look at the night sky, we're seeing a tapestry woven by stellar life and death. Every bright point of light exists because somewhere, sometime, a star chose to go out in a blaze of glory, and in doing so, lit the fuse for new beginnings. The universe writes its story in supernova, and we're living proof of their enduring legacy. The galactic environment is the ultimate stage director for star formation, scripting vastly different fates based on location alone. Imagine two stellar nurseries born from identical clouds of gas, one nestled near a galaxy's bustling core, the other drifting in its serene outskirts. Though they share the same raw materials, their stories will diverge spectacularly, shaped by forces far beyond their control. Near the galactic center, stars grow up in a cosmic pressure cooker. Ultraviolet radiation from supermassive black holes and dense star clusters bombards newborn protostars, stripping away their delicate gas envelopes before they can fully form. Gravitational tides, the relentless pull of billions of stars packed into a tight space, stretch and distort molecular clouds into bizarre shapes, triggering violent bursts of star formation. The result, short-lived stellar titans that blaze brilliantly and die young, seeding the area with heavy elements but leaving little time for planetary systems to mature. Contrast this with the galactic suburbs where quiet reigns. Here, far from the core's chaos, gas clouds collapse at a leisurely pace, undisturbed by external pressures. Stars in these regions tend to be smaller, cooler, and far more stable like our Sun, which likely formed in a similarly placid neighborhood, without the relentless radiation and gravitational harassment of the inner galaxy. These stars enjoy extended childhoods, allowing protoplanetary disks to coalesce into orderly solar systems. Some red dwarfs in these outskirts may burn for trillions of years, outliving the galaxy itself. But location isn't just about distance from the core. Spiral arms add another layer of complexity. As clouds pass through these dense regions, the increased pressure squeezes them like a cosmic vise, igniting waves of star formation. The Orion Nebula, our closest stellar nursery, currently rides the edge of the Milky Way's local arm, a prime spot for star birth. Yet even this isn't static. Over millions of years, the rotation of the galaxy will carry these stars away from the arm's density, leaving future generations to form under different conditions. Then there's the influence of neighboring galaxies. The Magellanic Clouds, dwarf galaxies orbiting the Milky Way, have likely triggered star formation in our outskirts through gravitational nudges. In more extreme cases, galaxy collisions can unleash firestorms of stellar birth, as seen in the antennae galaxies, where entire spiral arms glitter with newborn clusters. These interactions remind us that no stellar nursery exists in isolation. Each is part of an interconnected web stretching across the cosmos. Astronomers map these environmental imprints by comparing star-forming regions across different galactic zones. Near the core, they find evidence of rapid, violent births, stars with unusual chemical compositions or extreme orbits. In the halo, they discover ancient stellar populations that have drifted far from their birthplaces, carrying clues about the galaxy's youth. Every star is a time capsule, its properties whispering secrets about the neighborhood where it took its first breath. So when we study a star's light, we're reading more than its personal history. We're decoding the story of its homeland, the bustling metropolis or sleepy village that shaped its destiny. From the frenzied core to the tranquil fringes, the galaxy writes its autobiography one star at a time, proving that in the cosmos, as in life, location is everything. The eighth cosmic crossroads might be the most consequential of all, the moment when a collapsing cloud of gas decides just how massive its newborn star will be. This isn't just about size, it's about destiny. A star's initial mass writes its entire life story before fusion even begins, dictating everything from its color and temperature to its death throws billions of years later. Imagine two protostars forming side by side in the same nursery. One gathers just 8% of our Sun's mass, becoming a dim red dwarf that will smolder quietly for trillions of years. Its neighbor, meanwhile, accumulates 50 solar masses, blazing blue hot and destined to explode before the first star even reaches middle age. This mass threshold isn't merely a difference of scale, it's a fork in the cosmic road where stellar fates diverge irrevocably. What tips the balance? It often comes down to a protostar's feeding frenzy. As gas spirals inward through a swirling accretion disk, competition is fierce. Some stars hog material, growing rapidly and shutting out smaller siblings. Others form in crowded neighborhoods where the gas supply gets divided into many modest portions. Magnetic fields play referee in this cosmic buffet, channeling flows of material that can either starve or stuff a growing protostar. Even turbulence matter's chaotic motions can prevent gas from settling onto any single star, leading to a cluster of lightweight suns instead of a few giants. The consequences ripple across galaxies. Massive stars are the universe's alchemists, forging heavy elements in their cores and scattering them in supernova explosions. Without these titans, there'd be no iron for planets, no oxygen for atmospheres. Yet they're also cosmic bullies, blasting nearby systems with lethal radiation. Their shorter lifespans, sometimes just millions of years, mean any orbiting planets have little time to develop life. On the flip side, small red dwarfs offer stability, some burning steadily for longer than the current age of the universe. But their dim light creates tight habitable zones, and many are prone to violent flares that could strip away planetary atmospheres. Our own sun sits comfortably in the middle, a yellow dwarf massive enough to warm Earth for billions of years, yet small enough to avoid self-destructive theatrics. This Goldilocks mass didn't happen by accident. It reflects the specific conditions in its birth cloud, where gas distribution and rotational forces struck a perfect balance. Had those conditions varied even slightly, we might orbit a star too hot or too faint for life as we know it. Astronomers see this mass lottery playing out across every stellar nursery. In the Tarantula Nebula, stars routinely form with over 100 solar masses, their intense ultraviolet light carving glowing cavities in the gas. Meanwhile, in quieter regions like the Pleiades, middleweight stars dominate, their gentler radiation allowing delicate protoplanetary disks to survive. Even more extreme are the so-called failed stars, brown dwarfs that never quite reach the mass needed for sustained fusion. These cosmic in-betweeners outnumber true stars in some galactic neighborhoods, silent witnesses to how fine the line is between stardom and obscurity. So when we look at the night sky, we're seeing the aftermath of countless mass decisions made in ancient clouds. Every star's brilliance, color, and longevity trace back to that pivotal moment when gravity parceled out gas like a cosmic dealer handing out cards. Some got royal flushes, the massive stars that shape galaxies. Others drew modest hands, the steady burners that might one day host life. And in that distribution lies one of the universe's great truths. Destiny isn't just written in the stars, but in the weight of the gas that formed them. At the heart of every young star's story lies a swirling, tempestuous stage, the protostellar disk, where the seeds of future worlds take shape. These vast, pancake-shaped rings of gas and dust don't just feed the growing star, they're cosmic workshops where gravity, turbulence, and magnetic fields battle for control over the birth of planets. Picture a whirlpool of debris stretching billions of miles across, with material spiraling inward like water circling a drain. But here's the twist: what happens in this disk doesn't stay in this disk. Its choices echo across millennia, determining whether a star will reign over a bustling planetary system or drift alone through the void. Some disks are models of cosmic efficiency, orderly, stable, and brimming with potential. In these tranquil environments, dust grains gently collide and stick together, growing from microscopic specks into pebbles, then boulders, and eventually planetesimals. Our own solar system likely began in such a disk, where just enough material escaped the sun's grasp to form Earth and its siblings, but other disks are chaos incarnate. Turbulence shreds them into clumps that collapse into companion stars, creating binary systems where planets must navigate the gravitational tug of war between two suns. The difference often comes down to temperature. Cooler disks tend to fragment, while warmer ones hold together long enough for planets to form. Magnetic fields add another layer of complexity. Like invisible puppet strings, they can transfer energy from the star to the disk, creating jets that blast material light years into space. These outflows act as cosmic pressure valves, stabilizing the disk by preventing too much material from falling onto the star at once. Without them, many protostars might gorge themselves into obesity, leaving no leftovers for planets. Yet these same magnetic forces can also create deadly spiral waves, density ripples that fling budding planets into their host stars or hurl them into the frozen depths of interstellar space. Astronomers have caught these processes in action using instruments like the Atacama Large Millimeter Array, which peers into the hearts of young stellar systems. In one remarkable case, they witnessed a disk around the star HL Tauri with concentric gaps, clear signatures of planets carving paths through the dust like snowplows. Other observations revealed disks torn apart by stellar siblings, their potential planetary systems stillborn. The more we look, the clearer it becomes. The architecture of every solar system is frozen music, a symphony of forces captured at this critical moment when disk dynamics wrote the rules for what would follow. This crossroads doesn't just shape worlds, it shapes possibilities. A stable disk might give rise to neatly spaced planets with stable orbits, while a chaotic one could produce eccentric giants that bully smaller neighbors. Some disks contain organic molecules, the precursors to life, that survive only if temperatures remain just right. Others, overheated by their stars, become sterile zones where complex chemistry is impossible. Our existence hinges on a protostellar disk that struck the perfect balance billions of years ago, threading the needle between order and chaos to create the stage where life could one day emerge. So when we search for exoplanets today, we're not just cataloging worlds, we're reading the memoirs of ancient disks. Each planetary system tells the story of its birth environment, a cosmic fingerprint revealing whether its infancy was peaceful or violent, solitary or crowded. The universe writes these stories in the language of angular momentum and turbulence, reminding us that even in the vastness of space, the smallest details can decide the fate of worlds. Stellar winds are the great sculptors of star-forming regions, shaping not just individual stars but entire cosmic neighborhoods. As a young star awakens to nuclear fusion, it doesn't just shine, it screams into the void. Charged particles stream outward at hundreds of kilometers per second, a relentless gale that pushes against the surrounding gas like a cosmic hand. These winds don't just blow idly, they carve out vast cavities in stellar nurseries, isolating pockets of star formation and cutting off supplies of fresh material. The result, a single massive star can dictate how many siblings it will have by the sheer force of its breath. Consider the Orion Nebula's trapezium cluster, where 4 brilliant young stars have blown a bubble nearly 25 light-years across. Their combined stellar winds have evacuated the central region, preventing further star birth there while compressing gas at the edges into new generations of stars. This feedback loop creates a ripple effect. Each wave of star formation triggers winds that shape the next. Some regions become stellar metropolises with hundreds of stars packed tightly together, while others end up with scattered, solitary suns, all because of how these early winds redistributed the cosmic raw materials. The mechanics behind these outflows are as fascinating as their effects. Magnetic fields channel the winds into narrow jets that can stretch light years into space, punching through gas clouds like cosmic blowtorches. Infrared telescopes reveal these jets glowing brightly, their paths etched by shockwaves where they collide with slower-moving material. In some cases, these outflows carry enough energy to reignite star formation in distant clouds, proving that one star's death rattle can be another's birth cry. But stellar winds aren't just about brute force, they're precision instruments. The angle at which a protostar's jets emerge can determine whether surrounding gas collapses into new stars or gets scattered into useless turbulence. Some bipolar outflows act like cosmic egg beaters, churning gas into dense knots ripe for gravitational collapse. Others blow unimpeded into space, wasting potential building blocks. This delicate balance explains why some star clusters appear in perfect symmetry, while others look like cosmic afterthoughts, their members flung haphazardly by the winds of their eldest sibling. The legacy of these winds extends far beyond star birth. By clearing away excess gas, they allow light from newborn stars to travel farther, illuminating distant corners of galaxies that might otherwise remain dark. They also enrich interstellar space with heavy elements, seeding future generations of stars and planets with the ingredients for complexity. Our own solar system likely formed in the wake of such outflows, its chemistry shaped by the exhale of long-dead stellar ancestors. So when astronomers study these stellar winds, they're not just watching gas move, they're witnessing the universe's self-regulation at work. Every gust, every jet, every carved cavity represents a decision point where the cosmos balances creation and destruction. The stars we see today are the survivors of this relentless pruning, their numbers and arrangements frozen echoes of ancient gales that once swept through their nurseries. In the grand tapestry of star formation, winds are the invisible threads that weave order from chaos, proving that even in the vacuum of space, nothing truly stands alone. Dark matter is the universe's silent architect, its invisible hand guiding the fate of stars from the shadows. While we can't see it, touch it, or even detect it directly, its gravitational influence weaves through every galaxy, pulling strings behind the cosmic curtain. Picture a vast, unseen scaffold stretching across the cosmos, its hidden mass bending the paths of gas clouds and nudging them toward collisions that ignite stellar birth. In regions where dark matter clusters densely, its gravity acts like a cosmic magnet, drawing ordinary matter into star-forming factories. Elsewhere, where dark matter is sparse, gas drifts aimlessly, never coalescing into the density needed to spark new suns. Take the Milky Way's halo, a sprawling sphere of dark matter enveloping our galaxy. Without this invisible framework, the spiral arms we know so well would unravel, their gas too dispersed to form stars at the rates we observe. But dark matter's influence isn't uniform. In places like the Bullet Cluster, where galaxies have collided, astronomers have mapped its distribution by watching how it bends light, revealing how it shepherds gas into pockets ripe for star formation even amid cosmic chaos. Meanwhile, in so-called voids, the absence of dark matter leaves galaxies isolated and starved of raw materials, their stellar populations aging without renewal. The mechanics are deceptively simple. Dark matter's gravity creates wells where ordinary matter collects, like water pooling in a basin. The deeper the well, the more gas accumulates, and the higher the chances of stellar ignition. But here's the twist: dark matter doesn't just set the stage, it dictates the script. In dwarf galaxies like Draco, where dark matter outweighs visible matter hundreds to one, star formation is sluggish, as if the density is too concentrated for gas to collapse efficiently. Contrast this with sprawling spiral galaxies, where dark matter's more balanced distribution fosters vibrant stellar nurseries along the arms. Perhaps most astonishing is dark matter's role in the universe's large-scale structure. The cosmic web filaments of galaxies stretching across billions of light-years traces the underlying scaffold of dark matter, its gravitational pull having shaped the distribution of all visible matter since the dawn of time. Stars don't just form randomly, they light up along these invisible highways, their births choreographed by a force we're only beginning to understand. So when we marvel at a star-filled sky, we're seeing more than points of light. We're witnessing the aftermath of dark matter's quiet guidance, a reminder that the universe's grand design is written not just in what shines, but in what hides in plain sight. The cosmos builds its brightest wonders on the foundations of the unseen. Chemistry silently governs the universe's stellar assembly lines, with the abundance of heavy elements, what astronomers call metallicity, acting as a hidden dial that fine-tunes star formation. Imagine two molecular clouds drifting through space. One is pristine, composed almost entirely of hydrogen and helium, relics of the early universe. The other is enriched with traces of carbon, oxygen, and iron, ash from long-dead stars. Though they may look similar, their fates will diverge dramatically. The metal-rich cloud collapses efficiently, its heavy elements acting like microscopic radiators, shedding heat and allowing gravity to pull the gas inward with ease. The pristine cloud, by contrast, struggles to cool, its atoms bouncing around too energetically to settle into the tight knots needed for star birth. This metallicity crossroads explains why the early universe was a far poorer star maker than today's cosmos. In the first billion years after the Big Bang, galaxies consisted of nearly pure hydrogen and helium. Without heavy elements to cool the gas, star formation was sluggish and inefficient, producing only massive, short-lived stars that quickly exploded, seeding the void with the first sprinkles of metals. Over eons, as generations of stars lived and died, galaxies grew richer in these heavy elements and star formation accelerated. The Milky Way's disk, for example, is a stellar factory partly because it inherited the chemical legacy of countless supernovae, each contributing ingredients that make future star birth easier. But metallicity doesn't just influence whether stars form, it shapes what kind. In metal-poor environments, gas struggles to fragment, often collapsing into single enormous stars. The Tarantula Nebula in the Large Magellanic Cloud, with its lower metallicity than our galaxy's average, is a testament to this, birthing behemoths like R13601, a star over 200 times the mass of our Sun. In metal-rich regions like the Orion Nebula, by contrast, efficient cooling allows gas to splinter into many smaller clumps, producing a bustling community of sun-like stars and red dwarfs. The implications stretch beyond stars to the planets that orbit them. Metal-rich systems are more likely to form rocky worlds, their protoplanetary disks stocked with silicon and iron. Some astronomers even suggest that life itself may be a metallicity lottery. Only stars born in sufficiently enriched clouds could host planets with the right chemistry for biology. Our Sun's moderate metallicity, for instance, provided just enough heavy elements to form Earth's iron core and the carbon in our DNA. Yet there's a paradox. Too much metallicity can stifle star formation as well. In galactic centers where supernova have flooded the gas with iron and nickel, dust grains become so abundant they block starlight, preventing the radiation pressure that normally triggers new collapses. It's a cosmic balancing act, just enough metals to cool, but not so many that they smother the process. Astronomers trace these chemical fingerprints across the cosmos. In distant quasars, they've detected the faint signatures of early, low metallicity stars. In globular clusters, ancient stellar relics reveal the gradual enrichment of the universe. Even interstellar dust, sparkling with metallic crystals, tells the story of how chemistry and starlight have danced together for billions of years. So when we gaze at a star, we're not just seeing a ball of plasma, we're reading a chemical recipe, a snapshot of its birth environment's elemental palette. The universe's grand cycle of star life and death is at its heart, a story of atoms learning how to build ever more complex structures, one generation at a time. Galactic collisions are the universe's most spectacular construction sites, cosmic pileups where entire galaxies smash together at millions of kilometers per hour, turning serene star-forming regions into chaotic stellar factories. When two galaxies meet, their interstellar gas clouds don't just pass through one another. They slam together like titanic ocean waves, compressing the gas to densities that ignite firestorms of new stars. The antennae galaxies, locked in a slow-motion collision 220 million light-years away, showcase this phenomenon in breathtaking detail. Here, twisted streams of gas and dust stretch across space like celestial ribbons, dotted with brilliant blue clusters, each a nursery where thousands of stars have burst to life in just the past few million years. Yet this frenzy isn't evenly distributed. Some regions become supercharged stellar assembly lines, while others are torn apart by gravitational tides, their star-forming potential scattered into the void. What makes these collisions such potent star makers? It's all about sudden, extreme pressure. Normally, molecular clouds resist collapse for millions of years, held back by turbulence and magnetic fields. But when galaxies collide, shockwaves rip through their gas, crushing it instantly into dense knots. Imagine squeezing a handful of snow. The pressure transforms loose flakes into a compact ice ball. Similarly, these cosmic shockwaves bypass the slow, steady processes of isolated star formation, forcing gas to collapse en masse. The result is starburst galaxy systems where star birth rates skyrocket to hundreds of times the Milky Way's pace. The tadpole galaxy's iconic tail, stretching 280,000 light-years behind it, glitters with such collision-borne clusters, a glittering trail of stellar breadcrumbs marking its violent past. But not all gas survives the encounter. Just as some clouds ignite, others are flung into intergalactic space by gravitational slingshots, becoming orphaned star-forming regions adrift in the darkness. The mice galaxies reveal this darker side of collisions. Their long, stretched tails contain gas too diffused to ever form stars, cosmic roadkill left behind by the encounter. Even more dramatic are galaxy centers, where supermassive black holes, stirred awake by the collision, blast surrounding gas with lethal radiation, quenching star formation entirely. These opposing forces, compression versus disruption, mean colliding galaxies become patchworks of stellar feasts and famines, their star-forming futures rewritten in a single catastrophic event. The aftermath of these collisions lingers for billions of years. When the Milky Way and Andromeda galaxies collide in 4 billion years, their spiral arms will shred into streams of stars, while their cores, dense with freshly compressed gas, will likely erupt in a final blaze of star birth before merging into a giant elliptical galaxy. Fossil evidence of such ancient mergers can be seen in galaxies like Messier 87, whose globular clusters tell the story of multiple cannibalized neighbors. These collisions don't just make stars, they reshape galactic ecosystems, dispersing heavy elements across vast distances and altering the trajectories of countless stellar generations. So while galaxy collisions are rare on human timescales, their impact is eternal. They remind us that the cosmos doesn't always build gently. Sometimes it takes a wrecking ball to trigger the most brilliant acts of creation. The stars we see today, even in quiet galaxies like our own, may owe their existence to ancient crashes we'll never witness, proving that in the grand tapestry of the universe, destruction and birth are often two sides of the same coin. Cosmic rays are the universe's silent rain, a relentless downpour of high-energy particles that shape star formation in ways we're only beginning to understand. These aren't just random particles drifting through space. They're atomic nuclei accelerated to nearly the speed of light, often by supernova explosions or active galactic cores. When they slam into a molecular cloud, they don't just pass through, they transform it. Like invisible chisels, cosmic rays ionize gas molecules, stripping away electrons and leaving behind a trail of charged particles. This ionization might seem insignificant, but it's anything but. It changes how gas behaves under gravity's pull, altering the very rhythm of star birth across entire galaxies. Take the Taurus molecular cloud, a relatively quiet stellar nursery. Here, cosmic rays penetrate deep into the gas, ionizing enough molecules to create a faint but crucial electrical conductivity. This conductivity allows magnetic fields to grip the cloud more tightly, slowing down collapse and stretching out the star formation process over millions of years. The result, a steady trickle of modest stars, none too massive, none too flashy. Now contrast that with the Carina Nebula, where intense cosmic rays likely from nearby supernova remnants flood the region. The ionization here is so extreme it heats pockets of gas, creating pressure that fights gravity. Some areas resist collapse entirely, while others, compressed by the surrounding turbulence, ignite into massive stars at a frenetic pace. It's a cosmic seesaw. The same force that stifles star formation in one place can accelerate it in another. The origins of these rays add another layer of intrigue. Some are local, born from supernova within our own galaxy. Others are intergalactic hitchhikers, traveling billions of light years before finally colliding with a gas cloud. The most energetic ones might come from quasars or merging black holes in distant galaxies, their fingerprints etched into the ionization patterns we observe. Astronomers have even found evidence that cosmic rays might help catalyze complex molecules in space, including some precursors to life. In the frigid depths of a molecular cloud, these high-energy particles could be the spark that turns simple chemicals into the building blocks of planets and eventually biology. Yet cosmic rays aren't just builders, they are also destroyers. In young protoplanetary disks, too much ionization can shred delicate dust structures before they have a chance to grow into planets. Some theories suggest our own solar system's architecture, with its rocky inner planets and gas giants farther out, might reflect the intensity of cosmic rays in its birth cloud. Too many rays and Earth might have ended up a waterlogged ice ball, too few, and it might have lacked the organic molecules needed for life. The more we study these invisible sculptors, the clearer it becomes. Star formation isn't just about gravity and gas. It's a symphony of forces with cosmic rays as the wild card, adding unpredictable flourishes to the score. From the tiniest protostar to the grandest galactic collisions, their influence is woven into the fabric of creation, proving that sometimes the most powerful forces are the ones we can't even see. The universe's first stars weren't just different, they were alien. Born in a cosmos without heavy elements, these primordial giants, called population 3 stars, were unlike anything we see today. Picture a world without planets, without dust, where the only raw materials were hydrogen and helium left over from the Big Bang. In this sparse, pristine environment, gravity worked with brutal efficiency, pulling gas into monstrous stars hundreds of times more massive than our Sun. These behemoths burned ferociously bright and died young, their supernova explosions seeding the universe with the first heavy elements: carbon, oxygen, iron, the very ingredients that would make future stars, planets, and life possible. Fast forward billions of years, and the story has changed dramatically. Today's star-forming regions are like cosmic recycling centers, brimming with elements forged in those early explosions. This pollution, as astronomers call it, might sound like a bad thing, but it's the reason stars like our Sun exist at all. Heavy elements act as cosmic coolants, allowing gas to shed heat and collapse into smaller, more stable stars. The result, a universe that shifted from producing short-lived titans to a diverse population of stars, red dwarfs that smolder for trillions of years, middleweights like our sun, and the occasional blue giant that still echoes the extravagance of the early cosmos. The evidence for this evolution is written in the stars themselves. Ancient globular clusters, relics of the early universe, are dominated by small, metal-poor stars that have burned quietly for over 13 billion years. In contrast, young open clusters sparkle with a mix of sizes and compositions, their chemistry reflecting generations of enrichment. Even within single galaxies like the Milky Way, we see gradients, older stars in the halo with minimal heavy elements, younger ones in the disk rich with metals. It's a timeline of cosmic history etched in starlight, but time's influence doesn't stop there. The rate of star formation itself has slowed across the universe. In its youth, the cosmos was a frenetic factory, churning out stars at a pace 20 times faster than today. As galaxies exhausted their gas reserves and dark energy pushed them apart, the era of peak star formation passed. We now live in what astronomers call the cosmic afternoon, a quieter period where new stars are still born, but the great age of construction is winding down. Yet even now, the universe finds ways to surprise us. In distant galaxies, astronomers have spotted pockets of extreme star formation starbursts triggered by collisions or supermassive black holes that briefly revive the frenzy of the early cosmos. These flashes of brilliance remind us that while the rules have changed, the universe's capacity for creation endures. From the first, lonely giants to the sprawling stellar metropolises of today, every epoch has written its own chapter in the story of star formation, proving that time itself is the ultimate architect of the cosmos. Stars in dense clusters don't just share space, they shape each other's destinies through an invisible web of feedback loops, where every newborn sun alters the fate of its neighbors. Imagine a stellar nursery packed so tightly that the radiation from one star heats the gas another star is trying to gather, or where the fierce winds of a massive young star blow away the raw materials its smaller siblings need to grow. This is the 16th cosmic crossroads, where stars become both creators and destroyers in their own birthplaces, weaving a tapestry of interdependence that decides whether a cluster will flourish or fade. Take the Archer's cluster near the center of our galaxy, a dazzling metropolis of young, massive stars crammed into a space just a few light years across. Here, the ultraviolet light from the brightest members ionizes surrounding gas, creating pressure that can either compress nearby clouds into new stars or evaporate them entirely. It's a stellar paradox. The same energy that triggers birth in one region might snuff it out in another. Meanwhile, supernova shockwaves ripple through the cluster, stirring the pot with bursts of energy that can reignite star formation in unexpected places. These feedback loops turn star clusters into cosmic ecosystems where balance is fragile and every player has a role, but not all clusters navigate this dance successfully. In some, like the doomed protocluster Westerlund 2, massive stars dominate so utterly that their combined radiation blows away the remaining gas before smaller stars can fully form. The result, a top-heavy population where giant stars blaze briefly, then explode, leaving behind a ghostly shell of stragglers. Contrast this with something like the Pleiades, where gentler stellar winds and modest radiation pressures allowed a diverse family of stars to emerge, some massive, some small, all coexisting in relative harmony. The difference between these outcomes often comes down to timing. If feedback effects synchronize perfectly, a cluster can self-regulate, creating waves of star formation that sustain it for millions of years. If they fall out of sync, the entire system can unravel. The most fascinating aspect of these feedback loops is their scale. What happens in one corner of a cluster can reverberate across light years, like dominoes tipping in slow motion. Astronomers have observed triggered star formation in places like the Orion Nebula, where the birth of one generation of stars compresses nearby gas, sparking the next. These cascades can create nested generations, stellar siblings with age gaps of just a few million years, their lives intertwined from the moment they ignite. Yet feedback isn't just about destruction or creation, it's about transformation. The heavy elements forged in massive stars' cores get blasted into space by their winds, enriching the surrounding gas with the building blocks of planets and life. A cluster that thrives becomes a factory for complexity, seeding future generations with the ingredients for rocky worlds and organic chemistry. One that collapses too soon might leave behind only sterile remnants. So when we look at a star cluster, we're seeing more than a random grouping. We're witnessing a conversation, a dialogue of light, wind, and gravity where every participant speaks and every word changes the story. The universe doesn't just make stars, it lets them remake each other, proving that even in the vastness of space, no star is truly alone. Black holes aren't just cosmic vacuum cleaners, they're master regulators, wielding power over star formation on scales almost too vast to comprehend. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, millions to billions of times heavier than our Sun. These gravitational monsters don't just sit quietly, they feast on surrounding gas, belch out radiation, and unleash jets of plasma at nearly the speed of light. And in doing so, they become unlikely architects of stellar destiny. When a black hole actively feeds, the energy it releases can heat galactic gas to millions of degrees, puffing it up like an overheated balloon. In this superheated state, the gas becomes too energetic to collapse into stars, effectively putting a cosmic pause on star birth across entire galaxies. The Phoenix Cluster, a galaxy group over 5 billion light-years away, showcases this effect in stunning detail. Its central black hole has inflated a bubble of hot gas so immense that star formation has ground to a near halt for millions of light-years around it. Yet in rare, almost paradoxical cases, these same destructive forces can trigger creation. When a black hole's jets slam into cooler gas clouds at precise angles, they don't always obliterate them, sometimes they crush them. Like a hammer striking metal, the impact sends shockwaves through the gas, compressing it into dense knots that ignite into starbursts. The galaxy Messier 51, with its elegant spiral arms, reveals this delicate balance. Near its core, the black hole's jets have carved out cavities in the gas, suppressing star formation in their direct path. But along the edges of these cavities, the compressed gas has birthed brilliant blue clusters of young stars, a fiery necklace strung along the jaws of destruction. The key lies in the black hole's feeding habits. A ravenous black hole, gorging on large amounts of gas, tends to blast its surroundings with enough energy to sterilize entire galactic regions. But when it nibbles more modestly, its jets act like precision tools, sculpting rather than scorching. Astronomers see this in galaxies like Centaurus A, where narrow jets have triggered star formation in specific filaments while leaving the rest of the galaxy untouched. It's a cosmic demonstration of balance. Too much power and creation is smothered, just enough and it's catalyzed. What's truly remarkable is how these processes echo across time. A black hole's outbursts don't just affect the present, they shape a galaxy's future. By regulating star formation, they control how quickly a galaxy consumes its gas reserves, effectively setting its lifespan. Some galaxies, like the massive ellipticals in galaxy clusters, have been left red and dead by their black holes, their gas too hot to form new stars, their stellar populations aging without renewal. Others, like the Milky Way, have black holes in a gentler phase, allowing star birth to continue in the spiral arms. So when we study these cosmic behemoths, we're not just observing destruction, we're witnessing the universe's most dramatic balancing act. Black holes don't merely devour, they curate, their influence weaving through galaxies like invisible threads, pulling tight in some places and loosening in others. They remind us that even the most violent forces in the cosmos can be agents of both endings and beginnings, their power measured not just in what they destroy, but in what they allow to be born. Some stars refuse to play by the rules, rogues that wander the galaxy alone, untethered to any cluster or stellar sibling. These solitary travelers didn't form in isolation. They were born in crowded nurseries, then violently ejected by gravitational chaos. Picture a stellar game of pinball, where young stars get flung into the void by close encounters with more massive siblings or the subtle tug of passing gas clouds. What's astonishing isn't just their exile, it's what these outcasts reveal about the hidden turbulence within star-forming regions. Take Aorighi, a blazing blue runaway star hurtling through space at over 100 kilometers per second. By tracing its path backward, astronomers found it originated in the Orion Nebula, likely kicked out by a gravitational slingshot interaction with another star. Its fiery trajectory isn't an anomaly, it's a clue. Rogue stars like this expose the gravitational undercurrents of their birthplaces, hinting at violent dynamics we'd never see if all stars stayed put. Some of these exiles even carry the chemical fingerprints of their original neighborhoods, like cosmic breadcrumbs leading home. But the real mystery lies in the outliers, stars so isolated they challenge our understanding of star formation itself. In the voids between galaxies, astronomers have spotted a handful of solitary stars with no obvious birthplace. These extreme wanderers might have formed in the debris of ancient galactic collisions, or perhaps in rare pockets of dense intergalactic gas. Their very existence forces us to reconsider the boundaries of where and how stars can ignite. The implications stretch beyond curiosity. Rogue stars act as probes, illuminating the distribution of dark matter through their trajectories. Some might even host planets, though these worlds would face a harsh existence, no neighboring stars to warm their skies, just endless darkness. Yet even in their loneliness, these stars contribute to the galaxy's chemical tapestry, eventually exploding or shedding material that enriches the interstellar medium. So while most stars form in bustling clusters, the rogues remind us that the universe thrives on exceptions. Their paths are scars of gravitational battles, their solitude a testament to the chaos lurking behind the serene beauty of the night sky. To understand star formation fully, we must account for these rebels, the ones that slipped the cosmic leash and forged their own destinies. Cosmic filaments weave through the universe like invisible rivers, channeling the raw materials of star formation across unimaginable distances. Picture these vast thread-like structures, some stretching hundreds of millions of light years, as the backbone of cosmic construction, their tendrils connecting galaxies in a delicate web. Within these filaments, hydrogen gas flows like water through a network of pipes, pooling in dense intersections where gravity takes over, compressing the gas into knots so tight they ignite into stellar nurseries. The Spiderweb Galaxy cluster offers a stunning example, its filaments glowing with the light of countless newborn stars, strung along the cosmic threads like pearls on a necklace. Yet not all filaments lead to such abundance. Their efficiency as star fuel highways depends on a delicate balance of factors. In regions where filaments intersect at just the right angles, gas collides and stacks up, creating pressure cookers for star birth. The Hercules supercluster showcases this perfectly, with multiple filaments converging into a bustling hub of stellar activity. Elsewhere, filaments stretch taut and solitary, their gas too spread out to trigger significant collapse. The difference often comes down to temperature. Cooler filaments allow atoms to move sluggishly, increasing the chances they'll stick together, while warmer ones keep particles too agitated to coalesce. Magnetic fields add another layer of complexity, acting like cosmic rails that guide gas along the filament's lengths. In the Perseus-Pisces filament, astronomers have observed these invisible fields aligning gas molecules into orderly streams, effectively turning the filament into a high-efficiency delivery system for star-forming material. Without this magnetic guidance, gas might diffuse chaotically, leaking out into the void before reaching its destination. It's a cosmic irony. The largest structures in the universe rely on some of the most subtle forces to function. What's truly mind-bending is the scale of this network. Filaments don't just link individual galaxies, they form the scaffolding for the entire cosmic web, the large-scale structure of the universe itself. The Sloan Great Wall, one of the most enormous known filament complexes, contains thousands of galaxies strung along its length, each one born from gas that once traveled these interstellar thoroughfares. Even our own Milky Way likely owes its existence to a filament that fed it gas billions of years ago, a silent river of material that continues to trickle in today, fueling new generations of stars. But filaments aren't just passive conduits, they're dynamic ecosystems. Turbulence within them can create pockets of density, like eddies in a stream, where star formation sparks unexpectedly. Shockwaves from supernova or galaxy collisions sometimes travel along filaments, triggering waves of star birth like dominoes falling across light years. And when filaments grow unstable, they can fragment, spawning not just stars but entire dwarf galaxies that orbit their larger hosts like satellites. So the next time you gaze at the night sky, remember, the stars you see are more than isolated points of light. They're the products of an intricate cosmic supply chain, their birth made possible by filaments too faint to see, too vast to comprehend, the silent architects of the universe's grand design. Dwarf galaxies are the quiet introverts of the cosmic neighborhood, small, unassuming, yet hiding profound secrets about how the universe builds stars. Unlike their grand spiral cousins, these diminutive systems struggle to hold onto their star-forming gas, their gravity too weak to prevent it from leaking away into the void. The result, star formation that sputters like a candle in the wind, flaring up briefly before fading into long periods of dormancy. The sculptor dwarf galaxy, a satellite of the Milky Way, epitomizes this struggle. Its star-forming history reads like a staccato burst, intense bursts of activity, separated by billions of years of near silence, as if the galaxy itself is catching its breath between creative spurts. Yet this inefficiency makes dwarf galaxies cosmic time capsules. Their slow, sporadic star formation means they've retained gas with chemical compositions nearly unchanged since the early universe. While larger galaxies like Andromeda churn through their gas, forging and recycling heavy elements with each stellar generation, dwarfs like Leo T still harbor pockets of pristine hydrogen barely touched by stellar alchemy. It's as if these galaxies froze in time, preserving a record of conditions when the universe was young and stars were rare. The ultra-faint dwarf Segway 1, for instance, contains stars so metal-poor they're thought to be among the first ever born, their composition mirroring the raw ingredients of the cosmos just after the Big Bang. The contrast with grand design galaxies couldn't be sharper. In majestic spirals, gravity's firm grip compresses gas into orderly arms, fostering continuous star birth. But in dwarfs, the rules change. Their low mass means supernova explosions, usually mere speed bumps in larger galaxies, can blow away huge fractions of their gas, shutting down star formation entirely. The Pegasus dwarf irregular showcases this vulnerability. Observations reveal vast holes in its structure bubbles blown clear by stellar winds, leaving behind empty regions where no new stars can form. It's a reminder that in the cosmic tug of war between creation and destruction, size tips the scales, but dwarfs aren't just failed star factories, they're laboratories for extremes. Their shallow gravity wells allow for bizarre stellar populations impossible in larger galaxies. Some, like the recently discovered Bedin one, host stars moving so slowly they'd be swallowed by the Milky Way's tides, their languid orbits a relic of gentler dynamics. Others, like the bursting dwarf Zwicky 18, defy expectations by suddenly igniting into ferocious starbursts, as if stirring from a cosmic slumber. These bursts, though rare, can transform a dwarf's destiny, converting it from a gas-rich recluse to a brief blaze of glory visible across intergalactic space. Perhaps most intriguing is how dwarfs challenge our definitions. The line between a star-forming dwarf and a globular cluster blurs in systems like Omega Centauri, too massive to be a mere cluster, yet too small to qualify as a true galaxy. These cosmic in-betweeners hint that star formation operates on a continuum, with size shaping but not strictly limiting a system's creative potential. Even more enigmatic are the so-called dark galaxies, dwarfs like Dragonfly 44, which seem to harbor hardly any stars at all, their vast reservoirs of gas mysteriously dormant despite ample raw materials. So while dwarf galaxies may lack the grandeur of their larger counterparts, they offer something far more precious, a glimpse into the universe's unpolished draft. Their fits and starts, their preserved primordial gas, their stubborn refusal to conform, all whisper secrets about how star formation works when gravity's grip is loose and the cosmic rulebook is rewritten. In the end, their greatest lesson might be this: in the cosmos, as in life, small packages often hold the most surprising gifts. Brown dwarfs are the universe's cosmic rule breakers, objects too massive to be planets yet too small to truly shine like stars. Stuck in this celestial limbo, they burn dimly with the faint glow of deuterium fusion, never igniting the full hydrogen fusion that defines a true star. Imagine a gas giant like Jupiter, but with 50 times its mass, radiating a deep crimson rather than reflecting sunlight. These strange objects force us to reconsider what it means to be a star, revealing that the cosmos doesn't always follow the neat categories we create. Take the Orion Nebula, a bustling stellar nursery where astronomers have spotted entire populations of brown dwarfs mingling with newborn stars. Some formed alongside their brighter siblings, while others seem to have emerged alone like cosmic afterthoughts. What's puzzling isn't just their existence, it's their uneven distribution. In regions like the Taurus molecular cloud, brown dwarfs are rare, appearing as lonely outliers. Yet in places like the Sigma Orionis cluster, they outnumber conventional stars, as if the cloud itself preferred manufacturing these dim curiosities over blazing suns. The mystery deepens when we examine how they form. Some brown dwarfs likely started like ordinary stars, collapsing from fragments of molecular clouds, only to starve before gathering enough mass to ignite fully. Others may have been ejected from their birth disks too early, like stellar runaways stunted in infancy. Then there are the rogue brown dwarfs drifting through space unattached to any star, their origins a complete enigma. These varied birth stories suggest that the line between planet and star isn't just blurry, it's a spectrum, with brown dwarfs occupying every shade in between. Their influence defies their dimness. Though they emit little light, brown dwarfs can have powerful magnetic fields, unleashing flares that briefly outshine their normal faint glow. Some even host their own planetary systems, proving that star-like processes can occur on a miniature scale. The brown dwarf 2-mass J2105-4946, for example, sports a disk of dust and gas where planets could be forming an entire solar system in microcosm. Yet the real revolution brown dwarfs bring is philosophical. Their existence forces us to confront the gaps in our understanding. Why do some clouds produce swarms of them while others make almost none? Is there a tipping point where a gas cloud decides to form brown dwarfs instead of stars? Each discovery peels back another layer, revealing a universe more fluid and inventive than our textbooks once claimed. So while they may lack the brilliance of true stars, brown dwarfs shine a light on something far more profound: the infinite creativity of cosmic physics, where even the failures redefine what's possible. Before the first stars flickered to life, before galaxies took shape, the universe wrote its grand design in a fraction of a second. Cosmic inflation, an exponential expansion that stretched space itself faster than light. This primordial explosion didn't just create room for stars, it engraved the blueprint for their formation in the very fabric of reality. Picture the cosmos as a canvas flung wide, its surface rippling with quantum fluctuations, tiny variations in density that, when inflated to cosmic scales, became the seeds of all future structure. The denser regions pulled in more matter through gravity, growing into galaxy clusters, while the emptier patches stretched into vast voids. What's astonishing isn't just the scale of this transformation, but its precision. Had these early density variations been slightly stronger, matter might have clumped into monstrous black holes, slightly weaker, and gas could have spread too thin to ever coalesce into stars. The legacy of inflation is etched across the night sky. When astronomers map the cosmic microwave background, the afterglow of the Big Bang, they're seeing those primordial density variations frozen in time, patterns that would later dictate where stars would ignite. The Great Wall of Galaxies, the sculptor void, even the Milky Way's position in the cosmic web, all trace back to those first trillionths of a second. It's as if the universe, in its infancy, whispered instructions that would take billions of years to execute. But inflation's influence goes deeper. By stretching space so violently, it ensured matter would be distributed in a delicate balance, clumpy enough to form stars, but smooth enough to prevent catastrophic collapse. This Goldilocks distribution is why some regions of space, like the Virgo cluster, teem with star-forming galaxies, while others, like the Boötes void, stretch hundreds of millions of light-years with hardly a single star. The same quantum ripples that birthed galaxies also set star formation on a timer, determining how quickly gas could cool and fragment. In a way, every protostar's struggle against gravity today is the echo of a decision made when the universe was smaller than an atom. Perhaps most remarkable is how inflation's fingerprints endure. The Planck satellite's meticulous measurements reveal that these ancient density variations follow a near-perfect mathematical pattern, one predicted by inflation theory decades before it was observed. This harmony between prediction and observation suggests that the universe's expansion wasn't random. It was a finely tuned mechanism, setting the stage for everything that followed. So when we marvel at a star's birth, we're not just witnessing local physics. We're seeing the culmination of a chain reaction that began when reality itself was less than a second old. The universe didn't leave star formation to chance. It planted the seeds deliberately, ensuring that when the time came, there would be light. The universe is a clock winding down, its stellar factories slowly running out of fuel. Right now, across the cosmos, galaxies are producing stars at just a fraction of their peak rates, a trickle compared to the torrents of star birth that lit up the early universe. The Milky Way, for instance, forms about one new sun per year, down from perhaps 10 times that in its youth. This isn't a temporary slump, it's an irreversible trend. Every generation of stars locks away more gas in stellar remnants, white dwarfs, neutron stars, black holes, and flings more into the void through supernova winds. The raw materials for star formation aren't being replenished. Like a fire consuming its last logs, the cosmos is burning through its finite supply of hydrogen. Projections paint a stark future. Over the next 100 billion years, star formation will continue its gradual decline. Spiral galaxies, having exhausted their gas reserves, will fade from blue to yellow to red as their last massive stars die off. Dwarf galaxies, already clinging to scraps of gas, will fall silent first. Even the great reservoirs of intergalactic hydrogen, the universe's backup fuel supply, will grow too diffused to collapse into new stars. By 1 trillion years from now, the final stellar nurseries will flicker out in the most massive galaxies, their last protostars igniting in isolation. The era of star formation, which began 13 billion years ago with population 3 behemoths, will close with a whimper, a few scattered red dwarfs smoldering in the darkness. Yet this twilight holds surprises. Some galaxies may experience brief, final bursts of creativity. When elliptical galaxies collide in the distant future, their combined gas could spark one last generation of stars' cosmic encore performances in an otherwise darkening theater. Even more intriguing are the so-called frozen stars that could form in the far future. As the universe expands and cools, the threshold for nuclear fusion rises. In 100 trillion years, the coldest, densest gas clouds might collapse into strange, slow-burning stars fueled by quantum tunneling rather than classical fusion. These hypothetical objects would glow faintly for eons, stretching stellar longevity to its absolute limits. The end of star formation doesn't mean the end of light. White dwarfs, though no longer fusing elements, will radiate heat for trillions of years, their slow cooling providing a dim but steady glow. Collisions between stellar remnants, neutron stars merging, black holes accreting could flare up occasionally, brief fireworks in an otherwise silent sky. And the rarest of all, quark nova or dark matter annihilation events, might punctuate the darkness with unpredictable brilliance. But these will be exceptions in a cosmos where the steady rhythm of star birth has ceased. What's most profound is the timescale. 1 trillion years is to human history what a human lifetime is to the blink of an eye. The universe is still in its stellar adolescence. We live in the brief golden age where stars are plentiful and the night sky is vibrant. Future civilizations, if any survive, will inherit a vastly different cosmos, one where stars are relics and the Milky Way is a ghost of its former self. Their astronomy will be the study of dim embers and fading echoes, their night skies devoid of the stellar tapestries we take for granted. So when we look up at the stars tonight, we're witnessing something fleeting, a phase of cosmic history that won't last forever. The universe writes its stories in starlight, but like all stories, this one has an ending. The great stellar era will pass, leaving behind a colder, darker, but no less fascinating cosmos, one where the memory of star formation lives on in the frozen architectures of dead galaxies and the patient dance of remnants circling in the dark. Peering into the heart of a stellar nursery is like trying to read a book through frosted glass. The very dust that births stars also hides them from view. This is the observational challenge astronomers face every day. Cosmic gas clouds that stretch light years across, dense enough to block visible light but transparent to infrared eyes. Enter the James Webb Space Telescope, our most powerful window into these hidden worlds. With its gold-coated mirrors and cryogenic instruments, JWST doesn't just glance at star formation. It pierces through veils of dust to reveal protostars still swaddled in their birth cocoons. One stunning example is the Orion Nebula's hidden treasure, a cluster of newborn stars JWST exposed in wavelengths invisible to Hubble. These aren't just pretty pictures, they're revolutionizing our understanding of how quickly stars gather mass, how disks fragment into planetary systems, and why some stellar embryos thrive while others fade. Yet every technological leap brings new puzzles. Take the mysterious green filaments webs spotted in the Carina Nebula, tangled strands of hydrocarbon molecules glowing eerily around young stars. No current model predicted their intricate structure or their role in star formation. Similarly, JWST discovery of fully formed galaxies in the early universe has astronomers scrambling to reconcile their existence with standard timelines of cosmic evolution. It's as if the universe hands us a magnifying glass only to reveal finer print we never knew existed. Ground-based observatories add another layer to the challenge. Radio telescopes like ALMA map the frigid outer regions of protostellar disks, where molecules like methanol and formaldehyde trace the chemistry of future planets. But coordinating these observations across different wavelengths, combining ALMA cold gas maps with JWST heat signatures, is like assembling a jigsaw puzzle where half the pieces come from a different box. The result, breathtaking advances like catching a protostar's magnetic field channeling material onto its surface in real time, paired with confounding gaps. Why do some disks show chemical complexity while others remain barren? The greatest hurdle might be time itself. Star formation plays out over millions of years, while we observe mere snapshots. Astronomers compensate by studying hundreds of nurseries at different stages, like flipping through a cosmic flipbook missing half its pages. Sometimes nature offers help. In the Large Magellanic Cloud, a nearby galaxy with low metallicity, we see star birth unfolding under conditions resembling the early universe. Other times, serendipity delivers like the chance alignment of a distant quasar whose light, passing through a star-forming cloud, reveals its molecular composition in exquisite detail. What keeps scientists pushing forward is the tantalizing promise that each observation rewrites the rules. The same dust that obscures also preserves, trapping starlight in intricate patterns that, when decoded, tell stories of magnetic fields, turbulence, and gravity's patient work. Every photon collected carries whispers from the cosmic cradle, and with tools like JWST, we're finally learning to listen. The universe may guard its secrets closely, but it also leaves just enough clues to keep us reaching deeper. Theoretical models of star formation are like intricate clockwork, precisely engineered to mimic the universe's grand design, yet forever missing some hidden gear that makes reality tick. Supercomputers churn out breathtaking simulations, tracing the collapse of gas clouds into protostars with algorithms that account for gravity, radiation, magnetic fields, and turbulence down to scales smaller than our solar system. These digital nurseries produce stars that, on paper, look perfect, spinning disks, flickering jets, and clusters that mirror what we see through telescopes. But then nature throws a curveball. Take the case of HOPS 383, a protostar observed by ALMA in the Orion Nebula. Simulations predicted it should be growing steadily as it pulled in gas from its surroundings. Instead, it was erupting in violent bursts, devouring material in fits and starts like a cosmic toddler with no table manners. These mismatches aren't failures, they're gold mines. Every discrepancy between model and observation forces scientists to ask, what ingredient did we forget? Sometimes the missing piece is subtle, like the way cosmic rays ionize gas at the edges of molecular clouds, subtly altering their collapse. Other times, it's something radical, like the recent realization that interstellar dust grains might be far more irregular in shape than previously assumed, changing how they absorb and scatter light during star formation. The spiral galaxy Messier 51 became a Rosetta Stone for this process when JWST revealed intricate dust structures around its newborn stars, patterns no simulation had replicated. The dialogue between theory and reality plays out in unexpected ways. On one hand, simulations predicted the existence of radiation-driven implosion, where massive stars' ultraviolet light compresses nearby gas to trigger secondary star birth. Observations in the Carina Nebula later confirmed it. On the other, nobody anticipated the collect and collapse mechanism until telescopes spotted chains of stars along the rims of expanding supernova bubbles, their formation timeline defying earlier models. It's a reminder that the universe isn't just more complex than we imagine, it's more complex than we can imagine. Perhaps the most humbling frontier is the role of chaos. Tiny variations in initial conditions, a wisp of gas slightly denser here, a magnetic field fractionally weaker there, can cascade into wildly different outcomes. Supercomputers run ensemble simulations, creating thousands of slightly varied star-forming scenarios to map these contingencies. The results, even with identical starting parameters, some digital clouds form tight star clusters while others produce scattered singletons. This unpredictability mirrors real nurseries like NGC 2264, where neighboring pockets of gas birth stars with wildly different sizes and spacings despite similar environments. The quest to bridge these gaps is driving a new era of hybrid science. Machine learning algorithms now comb through terabytes of telescope data, identifying patterns human eyes might miss and suggesting adjustments to theoretical models. Meanwhile, labs here on Earth recreate snippets of cosmic conditions using lasers to simulate shockwaves or plasma chambers to study magnetic turbulence. Each breakthrough, whether in silicon or steel, inches us closer to understanding why the universe favors certain stellar blueprints over others. What keeps astronomers up at night isn't the flaws in their models. It's the thrilling possibility that the next great discovery lies hidden in the mismatch. When simulations fail to explain an observation, it's not a dead end, it's a signpost pointing toward uncharted physics. The history of astronomy is written in these corrections, each one a reminder that nature's imagination will always outstrip ours. And so the dance continues. Theorists tweak their equations, observers peer deeper into the void, and the cosmos keeps revealing layers of complexity we're only beginning to trace. Every star is more than a cosmic furnace. It's a potential architect of life, its formations shaping whether planets will bask in stable warmth or endure chaotic extremes. Consider two stellar siblings born from the same cloud. One grows into a calm yellow dwarf like our Sun, its steady light bathing orbiting worlds in just enough energy to nurture chemistry. The other becomes a volatile red dwarf, prone to flares that strip atmospheres and bathe planets in lethal radiation. The difference between these fates isn't random, it's written in the crossroads of their birth, where subtle variations in gas density, turbulence, or magnetic fields set them on divergent paths. The chemistry of life begins in these stellar nurseries. When a star forms in a metal-rich cloud, one enriched with elements like carbon, oxygen, and iron, its protoplanetary disk inherits the ingredients for rocky worlds and organic molecules. The Orion Nebula, bustling with young stars, showcases this process. Telescopes have detected sugar molecules and alcohols swirling around infant suns, the raw materials for future biospheres. Yet not all nurseries are so generous. In metal-poor regions like the outskirts of the Milky Way, stars form with scant heavy elements, their disks likely yielding only barren worlds or gas giants devoid of solid surfaces. Life's potential hinges on these chemical legacies, determined billions of years before planets even take shape. Timing is equally critical. Stars born in crowded clusters face gravitational chaos, their planetary systems scrambled by close encounters. The HD 16600 system, where a star's planet's orbit perpendicular to its disk, bears scars of such violent youth. In contrast, solitary stars like our Sun emerge from quieter nurseries, their planets forming in stable, undisturbed disks. This piece allows for the delicate orbital resonances that keep Earth on a steady, life-friendly path, but the most profound crossroads might be longevity. Massive stars blaze brilliantly but die young, their planetary systems cut short before life can gain a foothold. Small red dwarfs, though frugal with their fuel, often bathe planets in tidal locks and flares. Middleweights like our Sun strike a rare balance, burning long enough for evolution to work, yet gently enough to avoid sterilizing their worlds. The universe is under no obligation to create life. Most stellar paths lead to dead ends, too hot, too cold, too chaotic. Yet in the quiet corners where conditions align, matter awakens. We are proof of that fragile miracle, children of a cosmic crossroads where gas and chance conspire to build a home. Human curiosity has always reached toward the stars, but today we stand at a threshold unlike any in history where our tools might soon touch the very nurseries we've studied from afar. Imagine a probe drifting through the glowing tendrils of the Orion Nebula, sampling the chemical soup of a protostellar disk in real time, or a telescope array so vast it captures the magnetic fields threading through a collapsing cloud like cosmic stitching. This isn't just science fiction, it's the trajectory we're on, with missions like the upcoming Habitable Worlds Observatory and interstellar concept studies like Breakthrough Starshot inching us closer to the cosmic crossroads we've only theorized about. The irony is profound. The same forces that birthed our Sun now beckon us to unravel their secrets. Every discovery about star formation reshapes our self-understanding. When JWST spotted organic molecules in a nursery 500 light-years away, it wasn't just a chemical detection, it was a mirror. Those carbon chains and water ice grains are the raw materials of planets, of oceans, of us. We're not just observers of this process, we're products of it, stardust that grew curious about its own origins. Future missions could turn these philosophical realizations into tangible breakthroughs. Picture swarm robots deployed in a molecular cloud's outer layers, mapping turbulence patterns too fine for telescopes to resolve, or AI analyzing real-time data from a star's accretion disk, predicting flare events before they happen. The challenge isn't just technological, it's perceptual. Star formation unfolds over epochs while human lives span mere decades. To truly comprehend it, we'll need new ways of seeing, tools that compress eons into patterns we can grasp. Yet exploration isn't just about answers, it's about better questions. Each time we've studied a stellar nursery up close, like Herschel's revelations about filament structures or Alma's snapshots of disk fragmentation, we've uncovered deeper mysteries. Why do some clouds birth planets readily while others resist? How do magnetic fields communicate across light years to synchronize star birth? The more we learn, the clearer it becomes. These crossroads aren't just physical phenomena, they're conversations between gravity, time, and chaos, written in a language we're only beginning to decipher. What makes this moment extraordinary is the reciprocity. As we study star formation, we're also refining how to sustain life far from Earth, learning to harness plasma, manipulate magnetic fields, even engineer synthetic nebulae. The technologies we develop to explore these cosmic cradles might one day let us nurture new ones, extending the chain of creation that began 14 billion years ago. So when we look at the pillars of creation or the glow of a protostar, we're not just seeing distant wonders, we're glimpsing a future where humanity steps beyond observation to participation, where the species born from starlight becomes a shaper of stellar destinies in its own right. The universe wrote the first chapters of this story alone, but the next ones may bear our fingerprints. 28 cosmic crossroads might seem like isolated moments, but step back and you'll see their threads in a grand cosmic tapestry, each tugging on the others, weaving the universe's story in real time. Think of it like a celestial domino effect. A protostar's spin in one nebula might determine whether it fragments into twins, while the shockwave from a distant supernova could compress another cloud into a starburst. No star is an island. Its birth, life, and death ripple across light years, influencing generations yet to come. Take the Orion Nebula, where all 28 crossroads converge in a single stellar metropolis. Here, radiation from massive stars erodes nearby gas Crossroad 7, even as their gravity tugs dust into new clumps Crossroad 1. Magnetic fields channel some material into orderly disks Crossroad 10, while turbulence shreds others into chaotic knots Crossroad 5. The result, a dazzling variety: solitary suns, tight binaries, even rogue stars flung into the void Crossroad 17. This isn't randomness, it's the universe playing out every possible combination of its own rules. Zoom out further and the connections deepen. A galaxy's collision Crossroad 13 might flood it with metal-rich gas Crossroad 12, sparking a wave of efficient star birth that wouldn't have been possible in its primordial youth. Those new stars, in turn, seed future planets with carbon and oxygen Crossroad 27, while their eventual supernova enrich the next stellar generation. It's a cycle where every ending fuels a beginning and every choice branches into endless possibilities. What's humbling is how fragile this balance is. Alter one variable, say, the strength of cosmic rays Crossroad 14, or the timing of a black hole's outburst Crossroad 18, and entire galactic narratives rewrite themselves. The Milky Way's spiral arms, Earth-stable orbit, even the chemistry in our cells all trace back to a chain of cosmic decisions made billions of years ago. We're not just observers of this process, we're products of it, living proof that amid infinite diverging paths, the universe sometimes chooses threads that lead to complexity, to curiosity, to light. So when you gaze at the night sky, remember, those pinpricks of light aren't just stars. They're endings and beginnings, consequences and causes, all whispering the same truth: the cosmos thrives on connection. Every flicker, every shadow, every silent expanse is part of a story still being written, one crossroads at a time. From the first whisper of gravity pulling atoms together to the final, fading embers of star formation trillions of years from now, these 28 cosmic crossroads weave the grand narrative of our universe, a story written in collapsing gas, turbulent magnetic fields, and the delicate balance of chance. Each star we see is more than a point of light. It's the culmination of countless decisions made in the darkness, where the slightest variation could have led to an entirely different cosmos. The massive blue giants that seed galaxies with heavy elements, the steady yellow suns that nurture life, even the failed brown dwarfs that glow faintly in isolation, all owe their existence to these pivotal moments where physics, chemistry, and chaos converged. But this story isn't just about the stars themselves. It's about the planets that orbit them, the chemistry they forge, and the fragile conditions that allow curiosity to arise. The iron in our blood, the calcium in our bones, the silicon in our technology, every atom heavier than hydrogen was forged in the heart of a star, then scattered across space by supernova or stellar winds. Our very existence hinges on a chain of cosmic events so precise, so interconnected that it's humbling to trace them back. A molecular cloud that fragmented just right, a protostellar disk that resisted chaos long enough to form orderly planets, a galactic neighborhood quiet enough to avoid sterilization by radiation. We are the products of a universe that chose, at every crossroads, the paths that led to complexity. And the journey isn't over. Every telescope pointed at a stellar nursery, every simulation run on a supercomputer, every probe launched into the void adds another piece to this infinite puzzle. The James Webb Space Telescope's revelations about early galaxies, the Atacama Large Millimeter Array's snapshots of planet-forming disks, even the theoretical breakthroughs that redefined how we think about magnetic fields, all these are chapters in an unfolding epic. For every mystery solved, like the role of turbulence in star formation, a dozen new questions emerge, like the enigma of rogue stars or the origins of those eerie green filaments in the Carina Nebula. So tonight, when you step outside and look up, remember, you're not just seeing stars, you're seeing the aftermath of ancient choices, the echoes of cosmic collisions, and the silent work of forces we're only beginning to understand. Each flicker of light is an invitation to wonder, to question, and to keep exploring. The universe has given us its blueprint in starlight. It's up to us to keep reading. Now it's your turn. Which of these cosmic crossroads fascinates you the most? Is it the violent beauty of supernova-triggered star formation, the delicate dance of magnetic fields, or something else entirely? Drop your thoughts in the comments below. I love hearing your perspectives, and if you want to join me on more journeys through space's greatest mysteries, hit that subscribe button and ring the bell so you never miss an upload. The cosmos is vast, unpredictable, and endlessly surprising. Together, let's keep uncovering its secrets one star